I'm Anil Kumar, and in this video we will learn, rather understand, characteristics of tan function. So you have seen sketch of a tan function. I'll just draw that here for you, and while drawing I'll discuss some important things which we should keep in mind. Tan function has discontinuities. Like sine and cosine, they are continuous functions. Their domain is all real numbers. However, in tan, we have discontinuities. Do you know why? Well, the discontinuities are at minus pi by 2, plus pi by 2, and odd multiples of pi by 2. Right? So that is where we have a discontinuity. We rather have a vertical asymptote at these points. Another thing which you will notice is for tangent functions that they have periodicity of how much? It is not 2 pi, it is just pi, right? So periodicity for tan function is just pi, not 2 pi. So graph of the function is kind of like this. It goes like this and then turns, passes through origin and approaches infinity. And this pattern is repeated. Right? Now, so basically what we have here is, so it will be repeated here also, again and again this pattern is repeated. This should have been longer, but since I ran out of space I just squeezed it in. So here we have a function which is kind of like this. Now let me fill in the values. It's kind of a reminder for you. I'd like you to fill in yourself along with me. Now on the x-axis we could have x, but I'm preferring to have angle theta. Now this theta, I'm taking it in radians for this video. Here we have 0, and this point for us is pi by 2. This point, the 0 is at pi. And then at 3 pi by 2 we again have a vertical asymptote. On the left side of 0 we have vertical asymptote as minus pi by 2, a 0 at minus pi, and so on. Right? So that is how it should be looking like. Now why do we get a graph like this? That is a question which some students will always be wondering about. Let me share that part also. So what I will do here is sketch another system, coordinate plane with x and y on it. The reason for my taking theta is so that I could show you the relation between these things. So on a coordinate plane we have x and y. Trigonometric functions are called circular functions, right? Circular functions, you have a reason for it. We are considering movement along a circle, and if this movement is counterclockwise, we say that the angles are positive. But if this movement is clockwise, we say the angles are negative. And what are the angles? How do we get them? A point here on a circle, let us say, is xy. Now as the point moves from the initial position, you will notice that y value increases, correct? And x decreases. And therefore, tan, which is what? Which is ratio of y and x basically, correct? So if I actually join this point with the vertex, what I get here in the center, the angle subtended by the point and the horizontal x-axis is theta. And this angle theta is being represented there. Correct? So, to begin with, the point, let's call this point P, is at this position, theta is 0. That's the starting point, right? When theta is 0, then y value is 0. So 0 divided by x will be tan theta, which will be 0. So let's write it down separately. We are looking for the function tan of theta, which is basically ratio of y and x. So what we see here is, if we move counterclockwise, then the angle is positive. So if I move counterclockwise, what happens? Value of y increases and x decreases. And both are positive in quadrant 1. Is it okay? So in quadrant 1, what you notice is, quadrant 1 is from 0 to pi by 2, right? This angle, as far as theta is concerned, will be pi by 2, and this angle will be 0 for theta, right? So in quadrant 1, y increases, x decreases. So therefore, we have this graph which is increasing for tan. So I'm writing here function f of x equals to tan theta. So the value of tan theta increases. What happens as you approach pi by 2? You're approaching x is approaching 0. Anything divided by 0 is uncertain, it's not defined. So we have a vertical asymptote at pi by 2. And just before that, value is extremely large. So that explains this part of the graph, right, in the first quadrant. So as far as the domain is concerned, pi by 2 is not in the domain of your tan function, right? Now, as we move towards quadrant 2, what happens? In quadrant 2, the value of y starts decreasing, right? So here y starts decreasing, x starts increasing. However, the value of y is positive, but x is negative now. Do you see that? So in quadrant 2, the situation is that y is decreasing, x is increasing, but x is negative. So the ratio is going to be negative, and that explains the negative part in quadrant 2. So quadrant 2 is still this place, right? This one is quadrant 1. And then up to here, we have quadrant 2, correct? But again, as we approach pi, then at that point, y value becomes 0, right? Y value becomes 0. So here, you have a 0 for tan. So in this case, tan is negative, and negatively large, starting with, approaching 0 as shown here. Now as you go to quadrant 3, then what happens? In quadrant 3, both x and y values are negative, right? So if you have a point here, x is also negative, y is also negative, right? So in quadrant 3, both x and y are negative, therefore tan is positive. This is the part which is positive. Do you see that? So it changes from 0 to a positive value, correct? And so in quadrant 3, we see that tan is positive. Let me write down positive in quadrant 3. So what we found was that tan is positive in quadrant 1 and in quadrant 3, but negative here. Similarly, you will find that it is negative in quadrant 4, since y is negative but x is positive. So it's a ratio of negative and positive, so it is negative, correct? Now, let's get back to quadrant 3. Y increases, x decreases. Therefore, in quadrant 3, we find the value of tan increasing. As we move towards 3 pi by 2, right, the odd multiple of pi by 2, x becomes 0, right? At this position, x is 0. Infinitely large value of tan x is represented by the vertical asymptote. Now, then we move to quadrant 4. So when we move to quadrant 4, then what happens? X value starts increasing, y decreases. So we have in quadrant 4 negative value, since here and this function repeats, correct? So let me complete this. So here we have 2 pi. So as we move further towards 2 pi, which is one full circle, we notice that at this position y is again 0, right? And x is positive. So from here onwards, we move towards the positive value, and this cycle repeats. Do you see that part? It repeats again after 2 pi. But in tan, what we really saw is that the periodic function repeats after pi itself, and that is the reason why I just given a partial graph, right? So that really explains us how this graph represents the value of tan, right? In quadrant 4, we found both y and x to be positive. Oh, sorry, y to be negative, x to be negative, and so tan will be negative in quadrant 4. So that is the quadrant 4 part up to this place. Quadrant 4. This is quadrant 3 here, right? So let me write quadrant 3, which is here, right? So which is positive. I hope you understand this half. Now, how do you get the negative angles? If you move clockwise, then you get negative angles. So if you move clockwise, then it is negative angles. Do you see that? So these angles on the left indicates movement of the circular path along clockwise direction. Now here again, if you're moving from 0 away towards 90 degrees, negative 90 degrees, you find that the x value becomes almost 0 and we get a vertical asymptote at minus pi by 2. Well, go through this logic, you will understand how this graph is related with the value of tan. Now let us write down domain range zeros of the given function. Now clearly, the domain of our function is, that is, allowable theta values. All the theta values, theta is along the domain, is theta belongs to real numbers. However, theta is not equal to odd multiples of pi by 2. So odd multiples is 2n minus 1 times pi by 2. Okay, let me make some room here, or I'll draw a line so that we can now write the characteristics on the left side, right? So that becomes the domain for tan. Range is range of tan theta. The function itself is that tan theta belongs to real numbers, all values, correct? Interesting things which you saw here is zeros. Zeros are at multiples of pi, right? So we'll have all zeros at multiples of pi, 2 pi, minus 2 pi, and so on. So we can write this as k times pi, where k belongs to integers, which you normally write with z or sometimes with I. Correct? Now, interval of increasing. You will see in its domain, it increases all throughout. Do you see that? It always increases as you move from left to right, right? So that is how you can, in its interval. Important thing is there are few points which are not in the interval, right? That is the domain, right? So that is how you can write characteristics of tan function. You also know that tan function is ratio of sine and cosine, right? So if I have tan theta, it is ratio of sine theta and cosine theta. All these vertical asymptotes signify that cos theta is 0 at these points. Do you see that? And the zeros of tan are actually the zeros of sine, correct? That is how tan theta is related with sine and cosine, and these three primary trigonometric ratios will help us solve most of the questions relating to trigonometry or circular functions. I hope with this you get a fairly good idea about tan functions. Now let's move on and do some questions. Thank you and all the best.